All right, let's dive right into some more detail about NMR spectroscopy. But start with a little bit of a recap from the first mini lecture. So this is a very, very powerful spectroscopic technique that tells us a ton about the carbon-hydrogen skeleton. Now, that's information we really can't get from infrared or UV vis so much. So this is a very, very useful technique when it comes to identifying the structure of organic molecules. There's just a ton of information packed into an NMR spectrum. As we saw in the previous mini lecture, you can look at an NMR spectrum and you'll see that there are a certain number of what we call sets of signals. And the number of those sets of signals tells us everything about really how symmetrical that molecule is. So that's the first bit of information we've learned about. Now we're going to see how the position of each of those sets of signals, where they show up in the spectrum, tells us a lot about the molecule. Later on we'll see how the pattern of each of those sets of signals tell us something about how the molecule is put together. We'll learn about the integration or the integral for each set of signals. That tells us how many of each nuclei is associated with the set of signals. And then finally we'll wrap it up with something called the J value. So that is a boatload of information all packed into one spectrum. All right, as I said, this mini lecture is about the position of the set of signals. That's called the chemical shift, where the set of signals shows up in the spectrum. It's kind of a perplexing thing though, because, if nuclei are in the same electronic environment, and what do I mean by electronic environment? It's like, all right, we're thinking electrons, okay? A nucleus has electrons associated with it, and a nucleus is surrounded by other nuclei with other electrons surrounding it. So electronic environment is really about the electron density surrounding that nucleus. So, as we've seen, nuclei in the same electronic environment all sense the exact same magnetic field. They're called homotopic. Okay? They're identical by symmetry, and they all sense the same magnetic field. They are homotopic. That means they're going to show up in the same exact place in the NMR spectrum. Makes sense, but then why are we even doing this? Because, say, let's focus on the proton, the hydrogen, for a second. Don't all hydrogen have exactly that same electronic environment? That same energy gap that corresponds to where they'll show up in the spectrum? Because after all, when you look at it, that's Planck's constant. That's the magnetogyric ratio that associates with the nuclei. Those are both constants. This is a constant, and our magnet is our magnet. So wouldn't all hydrogens all show up at exactly the same place because this corresponds to this gap right here? Oop, I absorb energy, I show up in the spectrum, one line. I'm done. Well, no, and that's a good thing. It turns out that all nuclei don't have the same delta E. They don't all show up in exactly the same place because they are actually in different electronic environments, and therefore they sense slightly different magnetic fields. We call the magnetic field that the nucleus senses, the effective magnetic field. So while I have a magnet associated with my instrument, that magnet is a constant magnetic field, but those little nuclei feel something a little different based on the different electronic environment they're in. So this mini lecture is really about learning, well, why are these electronic environments slightly different? Well, in any case, since different kinds of nuclei actually sense different magnetic fields depending upon their environment, those are called heterotopic, and those will show up in different places in the NMR spectrum. So here's a picture of the NMR we have here at UMM in the basement, and there is the big honking magnet, and what I want to point out is that that's a constant. It is at 7 Tesla, but the external magnetic field associated with that magnet is not the same as the effective magnetic field that heterotopic nuclei feel. So let's dive into this. This is a good thing because that means different kinds of hydrogens and different kinds of carbons and different kinds of phosphorus in an NMR active nucleus. We generally are focusing on proton in this class. Basically, different kinds of hydrogens will then be in different electronic environments, feel different effective magnetic fields, and therefore show up in different positions. And that position is the chemical shift, abbreviated delta. And what you can see from this correlation chart is, for example, a CH3 shows up around 1 part per million, whereas a CH3 on an aromatic ring shows up at about 2 parts per million. What's up with that? Well, we'll learn in this mini lecture and the next. Maybe an easier way to drive home this point about how the different electronic environments impact where nuclei, in this case proton nuclei, show up in the NMR spectrum is illustrated in this correlation chart. So it's the same thing. Down here at the bottom we have our NMR spectrum scale. This is the part per million from 0 to 14. That's kind of typical for proton NMR. And what you can see is alkanes show up down here around 1, typically around 1 part per million. Something that has a nitrogen or an oxygen is a little bit further to the left. Aromatics are quite a bit different. They show up much further to the left, around 7 and 8, and so on and so forth. So what you can see is that you can see very distinct regions of the NMR spectrum depending upon the kind of electronic environment the nucleus is in. So let's look at this guy for a second. Here is an NMR spectrum. What can we see? Well, what we can see is that we have 1, 2, 3 sets of signals. Now I know this looks like 2 sets of signals. This is something that you'll get used to later on. We'll find out soon enough that those are all associated with one type of nucleus. Alright, so what do we have here? Well, we have something around 1. And if we have something around 1, that's really telling me that I probably have an alkane type structure. So I'm going to associate this right here with alkane, like CH2 or CH3 perhaps. Alright, what shows up around 4, 4.5? Well, what shows up around 4, 4.5? Certainly looks like it would be something associated with oxygens. Look at all those oxygens. So it looks like it's a hydrogen on a carbon next to an oxygen. So if I look at that, I'll bet you any money that this is an OCH something. Okay, because that's what my correlation chart tells me. So I've got alkane here, I've got OCH something here, and what's around 7 to 8? Holy cow, that is always bells and whistles for aromatics. So without knowing much NMR at all, I can say from the get-go, I have something like this, something like this, and something like this in my molecule. And that's a lot of information just in a few minutes. Alright, so that's the chemical shift, the position where these signals show up. But just restating what we've already learned, that nuclei in different electronic environments sense these different effective magnetic fields, and they're heterotopic, The question is why? What gives rise to this difference between the external magnet and what the nucleus actually feels? So that's what this one is. What the nucleus feels. Well, time for a bad analogy, but I hope it's a helpful one. It's cold. It's Minnesota. It's winter. So imagine two UMM students on, this one today, it happens to be 0 degrees. Here is UMM student dressed appropriately, and here is UMM student dressed maybe more typically, I don't know. But basically, if you look at these two UMM students, you can see that clearly one is going to feel the full brunt of that 0 degree weather a lot more than the other. They are both UMM students, but they feel the cold differently. So the analogy here is in NMR, that clothing that these two UMM students wear is akin to a coat of electron density surrounding the nucleus. So the UMM students are the nuclei. The outer garments they're wearing is the electron density. The cold is the external magnetic field. This is the clothing slash coat of electron density. Well, more or less. And this is what the nucleus actually feels. So I actually should just say that the localized magnetic field is just what's keeping you from feeling the cold. Bottom line is the effective magnetic field that the nucleus feels is impacted by both that coat of electron density and the strength of the magnetic field. Needless to say, if it were 70 degrees out, these two students would be feeling something differently. That's the strength of the magnetic field. All right, and this should make sense when you get back to thinking about the fundamental processes taking place in NMR spectroscopy. That as we expose a nucleus to a magnetic field, we are causing a difference in energy between the alpha state and the beta state. And that as the magnetic field increases, that energy gap that allows the transition from the alpha state to the beta state gets bigger. So the stronger the magnet, or I should say the stronger the felt magnet, the bigger the energy gap. So as we look at these effective magnetic fields, we have to come up with two new terms to help describe what the nucleus is feeling. A shielded nucleus has this humongous, wonderful coat of electron density around it. It would be like the UMM student that was on the left. It is completely protected from the brutal cold of the external magnetic field. So it has a smaller energy gap, as in this example, and therefore the delta E is smaller, and that means lower frequency, and this position for the absorbance is on the right side of the spectrum. Okay, so a shielded nucleus, smaller energy gap, right side of the spectrum. If I'm like the UMM student on the right, just in tank top and shorts, oh my God, I'm feeling almost the entire external field. That's a huge energy gap. Therefore, we're talking about a higher frequency transition, and that will then therefore appear on the left side of the spectrum, corresponding to much bigger energy transition. All right, so here's a spectrum. We have two sets of signals. That thing on the very far right is external to the sample. We get to ignore that. So we have two protons. One is in a completely different place, completely different chemical shift than the other. So what can we say about these? Well, the one on the left is experiencing the huge brunt of the external magnetic field. It is very much deshielded. Therefore, there's a big energy gap, and this is a higher frequency transition on the left side of the spectrum. This signal that's right about at 3 parts per million, well, that's shielded. It's protected from the external magnetic field to a great degree, and therefore it's a smaller energy gap. The terminology that we have to get used to is that upfield is shielded to the right, downfield is deshielded, and that's to the left. The other thing you need to just always keep in mind is that the higher energy transitions are on the left and the lower energy transitions are on the right. I want you to understand the transitions that are taking place that give rise to these different positions. Well, that's all fine and good, but what is impacting the shielding and deshielding? That's for the next mini lecture. Try to wrap your head around the transitions and the energy changes at the end of this one. But since that can kind of give you a headache, here is a little funny for you to go think about. And that's all for this mini lecture. We'll see you in class.